if you found what you like, then the most difficult step is already done.
So really, go for it. There's something in space that I think unites people. There's lots of countries involved there, and they all work together amazingly well. I think it's way more important than we realize. I'm hoping for a bit more women in the space industry because we are not that many, and sometimes when you see panels, it's all male, and you think, okay, aren't there any great women? And yes, they are. So I'm hoping for a more diverse space community.
And to go further to the moon, to Mars, and so on.
We really produce something which people want. The data our satellites deliver to our end users is something which makes a difference even to everybody's daily life, because every weather prediction you see on your smartphone, on the TV screen, does rely on the data we deliver. And being part of that process, of that organization, is great. My job is to make sure that the original user requirements of the National Weather Services are finally being met by the satellites being flown in space. A user requirement could be, for example, high-resolution wind speed. And requirements engineering makes sure that the final satellite, the instrument, the ground processing all work together such that the wind speeds which are produced meet the requirements of our users. I think Darmstadt, and especially the area, offers a lot for work-life balance. You can go, in 20 minutes you are in the middle of the Odenwald, in the forest. You can go hiking, you don't see anybody. I personally do a lot of mountain biking there, and I can even cycle to work. And on the other hand, if you want to see city lights, you drive 20 minutes and you're in Frankfurt. And if you want to go even further, you're at the airport and you can basically fly everywhere from there.
I work at UMetsat as a remote sensing scientist, and my focus is on sea surface temperatures and sea ice surface temperatures from satellites. So I've always been interested in science and the environment, but I wanted to do something that meant something and that actually helped people. So working at UMetsat gave me the opportunity to combine all of these different interests. I think the job I do here makes a difference in the world, as well as affecting weather forecasts. It's also important to understand a changing climate. So we need to know the best possible knowledge of our ocean and the ocean's health so that we can monitor it and then understand how this may change in the future.
So the most exciting and rewarding part of my job is obviously when we have a launch and we get the first telemetry into the ground segment we just built, and we have the first payload telemetry coming in and the first products coming out. This doesn't happen every year, but we are working several years towards such a target. I believe the job I do makes a difference, especially when you watch weather forecasts on the TV in the evening, which is made with images or data we provide from UMetsat. And also, for example, in the recent hurricane events in Florida, we provided support to NOAA to do their own forecast and see where the hurricane would go. So I really think it makes a difference.
Since the 1980s, OIP Sensor Systems has been an electro-optical partner for ESA, OIP developed custom-made high-performing optical payloads to provide images of planets in renowned missions, such as Proba 1, Mars, and Venus Express. Our compact visual monitoring cameras are used to monitor the effective performance of space mechanisms and to make scientific images to be studied down on Earth. OIP's spectrometers support ESA and other space partners in planet observation missions, such as Proba 5. Those spectrometers are also used by scientists to analyze the Earth, Mars, and Venus atmosphere on board of Altius, Nomad, and SWAR. If you are looking for high-performance visualization from Earth to space, OIP is your partner by excellence.
Space is part of our lives today, bringing many benefits. In the near future, space will become an even more important part of our lives. Bringing these benefits to us requires numerous technologies to work together. Space Application Services has been developing and delivering technology-enabled services, bringing the benefits of space to Earth for more than 30 years. We plan, prepare, develop, and operate equipment in space for our customers, such as the European Space Agency and NASA. Our strategy is to identify the right question, do the research, and develop the most suitable business solution. Today, we already provide anyone regular and frequent access to space. We open the door to research and manufacturing of novel products that do not exist on Earth. We train the astronauts of tomorrow, and we keep those working in space healthy and safe. We provide technology for in-orbit construction of low Earth orbit space stations and platforms. These will be the industrial powerhouses driving tomorrow's emerging markets, providing advanced materials and medicines. In the next decade, not only will we harvest the resources that are plentiful in space and which are depleted or scarce on Earth, but human settlements in space will use these resources to sustain their independent lives. Our technologies are improving life on Earth by predicting space weather events that can damage our electricity grids. Our astronaut exercise devices help to rehabilitate injured persons, and our robotics replace humans in hazardous environments. This is the near future. Space Application Services will be a part of it. We'll be happy to work on this future with you.
Travailler au pôle spatial Rotifers, c'est faire partie d'un espace de travail stimulant, offrant de nombreuses opportunités professionnelles. Milieu à haute plus-value, le pôle accueille des entreprises internationales dédiées aux applications spatiales. D'un côté, le centre ESSEC de l'Agence spatiale européenne à Redu. De l'autre, le parc d'activités économiques de Galaxia, développé par Idelux à Transine, qui comporte un centre d'entreprise, un incubateur de start-up, l'ESSEC Galaxia, l'Aerospace Center, le Galileo Integrated Logistics Support Center de la Commission européenne ou encore Rotifers. Ingénieurs, équipes pluridisciplinaires, start-ups et étudiants, des hommes et des femmes venus du monde entier s'y côtoient chaque jour au sein d'infrastructures modernes et innovantes, d'où naissent des projets de grande envergure, comme la gestion de l'opérationnalité des stations du système Galileo. Travailler au pôle spatial Rho-du-Transine, c'est faire partie d'un espace de mobilité situé au cœur de l'Europe. Entouré de grands axes routiers et le long de l'autoroute E411, le pôle bénéficie d'accès fluides et rapides depuis Namur, Bruxelles, Luxembourg et tous ses environs, en voiture et via les transports en commun. Travailler au pôle spatial Rho-du-Transine, c'est faire partie d'un espace authentique et naturel. Lieu de gastronomie et de patrimoine, la région entourant le pôle offre des occasions de sorties variées, telles que le festival de Chasse-Pierre, la foire agricole de Libramont, Libin et son musée Mudia, ou encore le village du livre de Redu, ses infrastructures sportives modernes, son cadre naturel propice aux balades et ses nombreux lieux touristiques comme Bouillon, Bastogne, Durbuy ou encore La Roche en Ardennes. Travailler au pôle spatial Rho-du-Transine, c'est faire partie d'un espace culturel porté par de nombreux centres urbains rapidement accessibles. Namur, Luxembourg, Liège, mais aussi Marches, Rochefort ou Libramont. Situé à seulement 40 minutes du pôle, Namur propose une vie citadine dynamique et de multiples activités culturelles, musées, théâtres, expositions ou encore concerts. Travailler au pôle spatial Rho-du-Transine, c'est faire partie d'un espace de vie de qualité pour développer un réseau de connaissances et fonder une famille. Logement à prix accessible, proximité de centres hospitaliers ou encore universités, haute école et écoles internationales sont autant d'atouts essentiels pour le bien-être des habitants de la région. Vous aussi, faites partie du pôle spatial Rho-du-Transine. Rendez-vous dès maintenant sur investinluxembourg.be.
My name is Nicolas Hartmann. I've been working for 3 months here at Rotifers Belgium in Transine as a ground system engineer.
My name is Lise Mouton and I am a recruiter and employer branding at Rotifers Belgium.
My background is engineering for 5 years, and the purpose of my job is to be sure that there are not any issues with the infrastructure on the Earth for the signal coming from the space.
Well, my background is a bachelor degree in human resources management, and I joined Rotifers Belgium 2 years ago, firstly with an internship of 1 year and now for the undefined contract.
I chose Rotifers because I really wanted to work in the field of space, and after my master thesis they asked me if I wanted to join the team, and I said yes directly.
First of all, I was afraid because I didn't know nothing from the space domain, but all the colleagues explained me their job, the duties.
I loved space for a long time now, so I wanted to work in not only for passion but to work. Every day is different because you don't know what really you have to do. Sometimes you have to plan to go on travel somewhere. Sometimes you have to work on a project.
I chose to join the company because they were open to have a junior profile.
What I really like here is a family-sized company, so it's not too big. So it's really easy to talk with people if you have an issue or something.
Everyone knows everybody. We are around the same age, and there is a good atmosphere, good ambience.
They have strong knowledge in the Galileo program, so for a young engineer as me, it's really interesting.
It's exciting to work for a space company. Everyone can have an access to join the space domain, so why not you?
Space and its exploration has fascinated humans since centuries. We send a few space probes in the solar system. We have even sent robots and rovers on Mars surface to explore it. And we even had a few city trips on the moon. We also have people living in space in the International Space Agency every day since a couple of years now. But the next step, the step further to learn more about space is definitely to go on Mars and to have manned exploration of Mars. How easy is it? Can we just take our lunch packet with us and go on Mars? No, definitely we cannot do that. Because we need, for our life, oxygen, water and food. And those elements represent massive amount of weight that we cannot just send on Mars. So we need to recycle the true waste to be able to sustain their life during space exploration, long-term space exploration. And this was the idea that was developed in the MELISA project by the European Space Agency 25 years ago now. In the MELISA project, the scientists are trying to build an artificial ecosystem that will allow recycling all true waste, urine, CO2, but also fecal materials if needed, to produce oxygen, water and food to sustain life of crew during years of mission. In the University of Mons, we are working on oxygen production based on cyanobacteria using different nitrogen sources. The University of Mons also participate to this space exploration and try to develop new methods to follow and optimize oxygen production by those microorganisms. Those projects also have a lot of application on Earth, because treating nitrogen waste, urine for example, using cyanobacteria is also a major challenge for space, but also for Earth application. If you want to learn more about this, just follow my talk about the MELISA project and the human's implication in producing oxygen in space using cyanobacteria. See you.
And today we are going to speak about life sciences and microgravity. But first of all, I would like to thank the engine of this event. This is Mons, who is an ex-senator and who is really the person who has been devoting a lot of time to be able to recreate this environment, almost as if we would be on Mars.
So going to Mars is not a simple endeavor. We know that there is quite a lot of technological and scientific difficulties, issues, and concerns that have to be raised and that have to be solutioned before we can really put humans on the surface of Mars. So the decision was to devote this specific session to the different aspects related to the human side. So humans are going to be at the forefront of our session today with outstanding speakers and also two excellent moderators, Jeremy and Kevin. So going to Mars is not an easy endeavor, and to make sure that astronauts are going to have a safe and productive mission to Mars, there are quite a lot of concerns and studies that have to be performed on their human health. My name is Sarah Batu, and I'm specialized in radiation impact on human health, trying to understand the impact of radiation and prepare our astronauts to go to Mars. And we thought for this session that the very best way to introduce this session would be through art, because this endeavor to Mars is not just a scientific and technological endeavor, but more than anything, a human endeavor and an artistic endeavor. Therefore, I'm extremely honored and delighted to introduce for this start of the session Mr. Daniel Van Quickelberghe, an opera singer. He's a Belgian tenor who graduated from lyrical arts from Ghent. And Daniel has played numerous leading roles in various operettas, musicals, and operas. And because of his tremendous stage experience, he is also a welcome guest at various concerts and performances everywhere in Flanders and in Belgium. And he's currently evolving under the guidance of a very prestigious lady, the former prima donna of the Flemish opera and voice coach, Erika Pauwels. And Daniel will bring a very emotional and special touch to this session. He will bring us his own a cappella version of The Rise to Mars. And The Rise to Mars is an hymn that have been composed 2 years ago in order to already be ready. As you know, a nation is qualified and characterized by its hymn. So Rise to Mars is an hymn to a planet, to a country we don't master yet, but we are ready to, and for which mankind is ready to take this endeavor. So I'm really happy to invite now Daniel Van Quickelberghe to perform Rise to Mars for us. Thank you very much.
Rise to Mars, men and women, dare to dream, dare to strive. Build a home for our children, make this desert come alive. There are challenges before our eyes that nature never knew, but the power of human enterprise shall take us true and true. Rise to Mars, men and women, dare to dream, dare to strive. Build a home for our children, make this desert come alive. Come along, raging nations, all together, hopeful spirits, bring an end to strife, for our future lies beyond the skies. Rise to Mars, men and women, dare to dream, dare to strive. Build a home for our children, make this desert come alive. Come along, all together, for a future, rise to Mars!
Thank you very much, Daniel. It was marvelous. Thank you very much. So I will make an interview of some students who are here. So can you present yourself and explain why you are here?
Yeah, So hi everyone, can I take it or? Okay. So my name is Emma. I'm still a student. Last year I obtained my master degree in biomedical sciences at the KU Leuven, and now I'm following a specialized master in cosmos exploration at the U Liège. And so I've chosen this extra specialization because I really like to study the human body in different atmospheres, which the one we're not used to. Like as a biomedical scientist, you're supposed to study medicines and work in hospitals, but I didn't really like that. I was more triggered by the whole space environment, and so that's why I'm also here now.
What do you think about Switch?
I don't know it that long, so I am. Yes, it's the first time I come to an event. I just found it on the internet and I subscribed and I'm here. So,
thank you. I will go to you. Can you present yourself?
Yeah. My name is Antonio. I'm Spanish, but I've been living in Brussels for approximately 10 years. And I used to work in the finance sector. And I'm on a sabbatical, let's put it that way. And I registered at KU Leuven at a master's on space studies. So I'm taking the courses there and I'm trying to, let's say I'm an engineer in my background. And I have always been very interested by space. So I'm trying to get acquainted with the sector in Belgium during these months.
Okay, fine. Thank you very much. So I think it's nearly time to begin our event. In 1 minute more, I think it's a little bit short, but I think we will begin. So this, and I will take my glasses. So and I will make a little introduction for the event. So good evening wherever you are, be it in Belgium or somewhere in the world. You are joining us from many countries: Guatemala, Armenia, United States, China, Morocco, Tunisia, Croatia, and many others. And that's great. That's really great. Space links us behind the borders. So as I said yesterday, this event is made for you, students and young professionals. And I will explain why. We have been into numerous universities with space experts. And we have observed that most of you love to see launching of rockets, love picture or movies on space, love to see astronauts working on a rocket, but many don't think to embark in a career in the space sector. It's strange, isn't it? It's strange and it's really unfortunate, as the sector is really in good shape and continues to actively recruit. So there is a problem. Where is the problem? You are attracted by space, but you don't think to make your career in the space sector. And personally, I see two reasons. The sector is too discreet and lives too much into its inner cycle. Second, the career perspective within space greatly expands today to numerous fields: medicine, we just heard, medicine, agronomy, biology, economy, defense, security, law, application, services. The diversity of its scope is not yet well known, and it's still difficult for students and young professionals to find an overview of the numerous possibilities of jobs in space. Reason why the super Belgian Switch team decided to launch the second edition of Switch to Space. An event organized on 8 days with more than 40 space experts. And like Sarah says, today is the day 2, the topic about life science and microgravity. The speakers will share with you their expertise, explain various opportunities of career prospect in space, They will share insight into their individual path, their job, their vision of the future of space in an accessible way, just to help you to make the best choice for your future career. And keep this in mind, keep it. In the next future, most of the job will be linked to space. Yes, switch to space, definitely it's the key that opens the path of the possible. Make your professional life exciting and enjoy switch to space. Thank you. And I will present now the switch team from the topic 2. It's Jérémy Rabineau, Kevin Tabury, and also Sarah, because Sarah is behind also the young. So Jérémy, as an aerospace engineer from ISAE-Supaéro in France, now is enrolled in a PhD in space physiology at the Université Libre de Bruxelles. Jérémy already had the opportunity to work on several experiments on the ISS and is passionate about the human aspect of space exploration. And I can say he dreams to becoming an astronaut. And Kevin Tabury. Kevin is a junior scientist at the radiobiology unit at the Belgian Nuclear Research Center, where he's leading hadron radiation-related project in the context of space and radiotherapy research. He's also currently combining his position as junior scientist with a PhD at the University of South Carolina in the United States. And Sarah, Dr. Sarah Batou, is head of radiobiology unit at the Belgium Nuclear Research Center. Her research focuses on the potential risk of ionizing radiation on health. Her work is performed in close collaboration with the European Commission, European Space Agency, Belgium and European universities, hospitals, and research institutes. She is invited professor at KU Leuven and guest professor at Ghent University, both in Belgium. In 2018, she won the B-Space Personality of the Year. It's me. and it's an award. And for her passion, she won the award for her passion and scientific work related to space biology. And Sarah went to Antarctica to monitor health changes in the extreme environment with high degree of isolation and confinement that parallels most closely long-duration human missions in space. I give the floor to the switch team, and they will present our speakers. You have one. No, thank you.
Hello, everyone. So my name is Kevin Tabury. I just wanted to welcome everyone and thank you for participating. We have today really an amazing speakers and topics. You will really enjoy it. I just wanted for myself just to tell you that actually everything is possible, whatever stage of your career you are. I'm actually started as a lab technician in space biology. And while being a technician, I did my master in industrial engineering with biomedical applications. And now I'm a junior scientist while combining a PhD, or finalizing with a PhD. So that is just to say that whatever you are at your stage, whether your studies or career, you can always switch to space.
Okay, so my turn. Thank you, Dominic, for the introduction. My name is indeed Jérémy Rabineau. By training, I am an aerospace engineer. And at the moment, I'm doing a PhD in space physiology, which just this shows you how diverse the sector of space is, and the importance to have multidisciplinarity, because you need to have some skills from different fields and to apply them to such into space, to what you want to do with space. I have a background in, I told you now, in space physiology. I apply it also to telemedicine via experiments on the ISS, but also during simulations of microgravity. I guess Vladimir Pletser will maybe tell you a bit about this later. So yeah, if you want to hear more about it, you have my contacts, so don't hesitate. But first of all, I'll give you a small introduction about today's topic. We're going to talk about life science and microgravity, but first, talking about life science, talking about physiology, we have to remind that our current physiology is the results of millions of years of evolution. It's like nature has made work like an engineer, testing things, removing what was useless and keeping what was nice. So step by step, our physiology has been optimized for survival. The small example I like to take usually is like, for instance, it's not possible to die by holding your breath. So which is a stupid thing. So nature has optimized in such a way that you will not die doing this. And all these evolutions, they occurred in a given environment. They occurred with the atmospheric pressure, they occurred with the field of gravity of the Earth, and so they are perfectly adapted to these conditions. Some of the things that maybe you wonder is, so if you take two snakes, so maybe you don't wonder because you don't know snakes too much, but anyway, some of them have the heart very close to the head, and some of them have the heart in the middle of the body. And this actually, you will see in 1 minute, is a consequence of gravity. Same thing for us, we have the heart rather on the top of the body, close to the head, and it's exactly because of gravity. It's because the heart needs to pump blood and to push it to the head, because in the head is the brain, and the brain is the most important organ in the human body. So if you come back to these snakes, you quickly understand that they don't live in the same place. And so you have the first one, the one with the heart close to the head, is living in the trees. This snake is able to go up on the tree, so to be in a vertical direction, whereas the other one lives in water. So there is not impacted by gravity in the same way. And it's for this reason that the heart is not at the same place. So just a small example to show you that our whole physiology is dependent on gravity. So when you remove gravity, this will have an impact. Why are we doing experiments in space, and why are we even wondering what happens when there is no gravity? It's because we're doing experimental science. One of the examples I like to take is, so you take a frog, you ask the frog to jump, you see the frog is jumping. So then you test something, you see, okay, I'm gonna do something, you cut the legs of the frog, so you just something you need to think about because you have no right to do it in real life. You cut the legs and you ask the frog to jump again, and you see that the frog is not jumping anymore. So you conclude, frogs here with their legs, which is obviously false. But so you need to fully understand something, a process, for instance, hearing in this case. You need to confront it to a diversity of different conditions. So it's what it's written here. And gravity is also one of the conditions you need to test. If you consider life, physiology, or biology as a black box, you have some inputs, some outputs, and there is a whole context around it. And gravity is part of this whole context. To better understand this black box, that is life, you can, for instance, put it in a field of 1G, put it in 0 gravity, put it maybe in 2G, 3Gs, and you see the response and you better understand physiology. So in the introduction, you saw that human beings have been designed to live in 1G, in this terrestrial gravity. This means that when you go to outer space, when you go in 0 gravity, some adaptations occur, and Vladimir will tell you a lot about this. So this is, I would say, a bad news for astronauts, but as I said, it's a good news for science because we get to know, you get to understand some of the process that happen. We invest a lot of money in space, and some people argue about it, saying that we need to spend this money to do other stuff. But actually, a report by NASA in 2015 said that actually the outcome of space investments is just huge. So you can count this in terms of lives that have been saved, in terms of jobs that have been created, but also in terms of revenue or in terms of costs that have been reduced. And I will just give you a few examples to show you that, yes, the ISS has cost $20 billion, but what we get from this is much more than this. So you take, for instance, osteoporosis. It's something that costs a lot of money. If you take just the USA and the European Union, it's an average of $60 billion per year. Then you have also other costs that are linked to osteoporosis. The total means that in the US and in EU, it costs $200 billion per year. That's huge. And we know that we can study osteoporosis in space. Again, you will learn a lot about this in the lectures in a few minutes. So if we learn anything about osteoporosis that can help us better understand it or find countermeasures, imagine we reduce by 1% the cost of osteoporosis in the world. That means $2 billion saving per year. So we deal again with huge numbers. Just with 1% reduction, you can save that amount of money. So it's very important. We do not do only science there. We also need to design systems so that, because the astronauts, you need to keep them alive if you want them to do science. So for this, we have a whole life support system to ensure that the astronauts can breathe a breathable atmosphere, that there is a good temperature and humidity and so on, that they can eat and drink, deal with the waste, etc. All these things are a bit special because you need to design them to work in very special conditions, the one of the ISS. And these small investments, these small technology demonstrations, then you can apply them on the Earth. We'll have a talk about this later on, talking about the MELISA projects, dealing with algae, with spirulina. What we learn here, we can apply on other sectors, like in architecture. You can build more eco-friendly buildings. You can increase food security. So the impact, again, is huge. And the last example I'm going to take, because there are numerous of them, but I'm going to take a last one. For instance, Air Liquide has designed a freezer for the ISS because you need to store your samples, blood samples, urine samples. You need to store them at -80 degrees. So the technology that they have designed for the ISS, now they have signed contracts to use them to transport liquefied natural gas. And the impact, again, is huge. It's approximately 100 million euros and a lot of CO2 emissions that are saved every year. So to sum it up, with life science and microgravity, it is possible to prepare future interplanetary exploration while at the same time contribute to our daily condition on the Earth. And which brings us to the topic of today, Moon, Mars, here we come.
And I have the pleasure and privilege to introduce our speakers. So today, as promised on the program, we have 4 amazing presentations with 4 amazing speakers. We're going to start the program with Professor Vladimir Pletser, who is currently Director of Space Training Operation at Blue Abyss. Before that, he was visiting professor at the Center for Space Utilization at the Chinese Academy of Science in Beijing, where he supported the microgravity research for parabolic flights, as well as the Chinese space station. He has as well 30 years of expertise and work as a senior physicist engineer at ISAE-Supaéro, where he developed microgravity payloads, such as the space labs. and was as well responsible for parabolic flight. You need to know that he performed 7,350 parabolic flights, which is actually a world record. He was as well Belgian astronaut candidate, where he trained at NASA, and with a master in mechanical engineering and a PhD in physics. With all his knowledge and expertise, he's going to give a talk on what happens to human body in microgravity. So the floor is yours.
And share screen. Yes, hello, good afternoon to everybody. Thank you for this introduction, Jeremy and Kevin. My name is Vladimir Pletser, as you said, and I will try to summarize in 15 minutes what is happening to the human body in microgravity. So the first thing that we need to understand is what is weightlessness. To be weightlessness is actually to be in free fall. And to be in free fall, gravity should be the only resulting force. You see there several trajectory for free fall trajectory to actually experience weightlessness. First one is vertical line, the second is a parabola, and the third is an ellipse. Basically, it's any kind of trajectory that is submitted only to the action, the resulting action of all gravity source in the universe. Why I'm telling you this? Well, to go to Mars, there are actually two ways to go to Mars. Either you apply a elliptic trajectory, you use elliptic trajectory, which is known as the Oman transfer trajectory from the Austrian scientist and engineer Oman, who devised it in the 1920s. This allows you to use, of course, a very low mass of fuel, which could be very useful sometimes, but also to give you quite a long time, because it would take you 6 to 8 months to go to Mars. If you see here on the little drawing, you see in blue the Earth orbit, and in red next to it, the orbit of Mars. You would need to go, let's say, from one point, this one here, to go to arrive eventually to Mars, which is an arc of an ellipse. And that would take you 6 to 8 months, depending on the orbital position. The second way would be to use a propelled accelerated trajectory, which would be much faster also. You would spend 2 to 3 months or so, but with the impact of using quite a high fuel mass. So as you know, the launch of mass in orbit is the most expensive part of the trip, because it takes about 20,000 euro, $20,000 is about the same order of magnitude per kilo to be launched. So you want to minimize, of course, the mass to be launched in space, but at the same time, you want also to minimize the exposure of the astronaut to microgravity and to radiation. So you want to have a compromise between the two. But let's not discuss that for the moment. Let's go to the physiological problem in microgravity. So basically, to talk about that, well, it would take several hours, and we don't have that. I have only here 15 minutes. I would like to summarize. There was a lot of written about that, several books and thousands of articles, and I would like to summarize everything within 4 categories. Basically, the first one is concerning body fluids and the cardiovascular system. You see the little drawing there. 4 schematics of a human person pre-flight here on the left part, so before launch, so still in 1G. The second one is in the air, it's the beginning of the 0G. The third one is after some time of adaptation in 0G, and the fourth one to the right, when the person is back on Earth or in a normal G environment. You see that the liquid column of mainly blood is normal at the beginning. So if you take the intracardiac pressure as being unity at the level of the heart, it would be double at the level of the feet and about 2/3 in the brain. So this is a normal gradient of blood pressure, which of course completely changed once you enter into 0G. What happened in 0G? Body fluids are no longer attracted downward and would tend to go upward, to come upward, to rush upward in the torso and the head, yielding an hypervolemia of blood in the upper body, which means that suddenly you will see the astronaut with having more blood into the head. You would see a puffy face, a more rounded and reddish face, and same time also would create an overpressure inside the brain and also other organs in the head, mainly the eyes as well. After some time, there is an adaptation. There is a natural elimination of the body fluids by urination, basically. So several days it would take. And then a new equilibrium is attained after a few days. The fourth little schematic there would represent an astronaut coming back to Earth or landing on Mars after a long trip in microgravity, where there suddenly body fluids are again attracted downwards, so toward the feet, and the astronaut would eventually adapt to a new G environment, but which would take some time, several days or weeks, to be readapted. So the problem that we encounter with this basically is that during the flight you have an overpressure in the head and in the eye, so what is called the spaceflight neuroocular syndrome, and which could induce something similar to the glaucoma that we know here on Earth. And after the flight, astronauts quite often suffer from orthostatic intolerance, and this you can try by yourself. When you wake up in the morning, the blood is evenly distributed in your body. You try to stand up very quickly, very sharply, and you will feel, maybe some of you will feel that the heart would not have sufficient time to adapt, and blood would not come to the brain, and you will faint a little. You will feel a bit fainted or lightheaded. Well, this is exactly what happened to the astronaut as well when they come back to a normal gravity environment. If we look at the heart itself, the cardiovascular system, well, the heart rate decrease when you enter into 0G. You see here as well in the little diagram here, at the level of the arrow, you see that there is a lengthening in time between two heartbeats. And at the same time, the blood pressure increase also. You see on the second line, the BP, blood pressure, you see that the difference between the minimum and maximum is increased in 0G. So this means that in 0G, in microgravity, the heart beats slower, but would pulse much more blood into the system. So the stroke volume would be increased in 0G. And this was a result of an experiment, several experiments conducted in parabolic flight and corroborated by experiment conducted in space as well. You see here, Pedro Duque on the Mir station, and above that, Belgian astronaut Frank de Win and myself being subject of this experiment of Professor André Aubert from the University of Leuven, the Catholic University of Leuven. Second category of problem is those that concern the balance, the orientation, and the vestibular systems. Basically on Earth, the body, the brain, has three sources of information to make sure that it knows in which position the body is in space. The first one is the in-ear vestibular system, which is a double system. The second is the visual system, the eyes, the vision, so which is a very strong source of information. And the third one, less known, but still important as well, that is called the proprioceptive system, which is made of the ensemble of all the muscles and the tendons in the body, mainly the neck, that gives the position, help to give the position of the head to the brain. The vestibular system is double, as I said, it's located in the inner ear. The first one is the autolytic system, which are small crystals of calcium carbonate that weighs on a membrane with nervous ending, where you see on the little drawing on top there. And if the subject would move his head, for example, bend it forward, as you see on the little drawing, then you see these otoliths, these little crystals that would slide forward as well, and that would touch, let's say, the endings of these nerves into this little membrane, and that would give the information to the brain that the head has moved forward, bended slightly forward. Same time, if you move your head sideways, the otolith would move sideways as well, and I would give this new information to the brain that the head has moved to the side. The second source of information is the semicircular canals, which are 3 canals in perpendicular planes we see here at the lower part of the picture, with liquid moving inside these canals. These canals are quite small, it's about a centimeter or even less. And if you move your head one direction, if you rotate, if you turn your head from the right to the left, like you would say no, for example, well, the liquid inside these little canals would be counter-rotating, would be moved in the other direction simply by inertia. And again, that would stimulate nervous ending in the canals, giving the information of the movement to the brain. Now, what happened in 0G? Well, there is a problem also, main one, that is called space sickness. In 0G, the vestibular system is no longer stimulated because gravity is no longer there to help this autolytic movement to move on this nervous membrane. But the visual and the proprioceptive system still work perfectly well. And this generates conflicting information that are sent to the brain, which at the beginning the brain can cope with, can restore the right information, but eventually, due to this overwhelming and too much information received, the brain would eventually not shut down, but would yield this as a conflict and would simply, start to empty the stomach. So you will feel first dizzy spells, and then you will feel some nausea, and then eventually you would be vomiting. This happens to a lot of astronauts. More than half of the astronauts would experience something like that. It usually gets better after a few days, so there's a few days of adaptation, but then the schedule of astronauts, of course, is kept very light on the first few days to make them sure that they can adapt to this new environment. After the flight, when they return to Earth or they land to Mars, on Mars, everything is coming back to normal rather quickly. The third problem is the bone demineralization, which is basically a major problem because in 0G, after a few weeks, we notice that the bone structure is losing a lot of minerals, mainly calcium and phosphorus. You see at the bottom of the picture of the slide there, two parts of the bone, well, two slides of bone. These are mice bone. On the left part is a normal bone, so very healthy bone. And on the right part, a bone that was submitted to several weeks or months of microgravity on the Mir station, if I remember correctly. So why do we see that? We don't know exactly. Basically, a human body would contain 1 kilogram of calcium, more or less. And the calcium has been measured to be approximately 100 milligrams per day. So this is relatively a lot. And this means also after a few months of 0G, this means that the astronaut could not return safely to Earth or land on Mars. Why is that? Because simply you would lose so much calcium that when you come back into a normal gravity environment, basically your bone will brittle and collapse and break, and the astronaut will simply fall like a little bag of broken bone and inside the skin bag, basically. So why this is happening? Well, there are two competitive processes, actually. The osteoclastic cell remove old bone cells, and the osteoblastic cell produce new bone cells. And in a normal gravity environment, you have a balance, an equilibrium between these two competitive process, except during childhood, where of course the child has to grow and there's more new bone that is created than the old bone being resorbed. And some experiments show that sometimes it's the osteoclastic cells that are prevalent, and some other experiments will show that it's osteoblastic cells that are prevalent. So we have sometimes conflicting results, and still the basic understanding is not fully there. And actually, the problem is much more complicated because it involves shocks and vibration on some bones. For example, the heel, when you actually walk or run, so the heel, when impact the ground, will give vibration that would help also to not calcify, but to keep, let's say, the bone structure as being strong. We notice as well that the upper body bones tend to recalcify, while the lower body bones tend to lose more calcium. Why is this? We still do not understand as well. As Jeremy mentioned also, it resembles a sickness that affects elderly people on Earth, which is called osteoporosis. So it's very interesting also to study this kind of problem on astronauts, because usually astronauts are healthy people in middle age, let's say in the 30s or 40s, and very in good health, basically. And that gives you a very good image of what is happening to the human body submitted to a 1G environment for 50 or 60 years, and then condense that you can study that on an astronaut submitted into a 0G environment for a few weeks or a few months, up to 6 months, for example. So basically, to combat this, we need drastic countermeasure, like 2 hours per day of exercising, or we need artificial gravity, basically. You see here at the lower right part, you see Dutch astronaut André Kuipers training on, well, let's say running on a treadmill on board the International Space Station. The fourth problem, and this is another major problem as well, is the immunodeficiency. In 0G, after a few weeks, it was observed in astronauts that there is a dysregulation of the immunological response, and the latent herpes virus that we all have inside our nervous system is mainly reactivated. So astronauts are commonly subject to this little herpes accident that they would have on their face, on their lips, and so on. So the long exposure to 0G induce a reduction of the T lymphocytes, which are the white blood cells, so the T lymphocyte counts that intervene in the immune response and in antibodies production. It attenuates the cytotoxin function, so basically the function of killing pathogens that are attacking the human body. And it reactivates any kind of viral infection. So it's not only a virus, but not only the herpes virus, but any kind of other virus as well. And the interest for this type of research is very high, because understanding the human's defense mechanisms and the role of gravity, or the role of microgravity, the absence of gravity, can shed light, can help the understanding of the fundamental properties of the immune system, which is, of course, of paramount importance, especially in these days, to try to understand how the human body reacts to viral infection, like the COVID-19 that we know today, or also the HIV/AIDS virus as well. So to conclude, the human physiology research must continue in microgravity. Of course, not only in real microgravity, but also in simulation. You see there the bed rest analog. This is the top picture in the slide, where you have patients lying down in bed with the head down. So the bed is tilted 4 to 6 degrees head down, and they would stay in bed for several months. That would simulate the headward shift of the body fluids. We do research also on parabolic flight. That allows to recreate 0G gravity for 20 seconds on board laboratory aircraft. And we do also moon gravity, moon parabola, that gives moon gravity for 25 seconds and Mars gravity for 30 seconds. We study as well human physiology in 0G and in reduced gravity. And there are also a lot of experiments on human physiology on board orbital space station, like the International Space Station now, in the future, the Chinese space station, and also the future Gateway moon station. We need to develop countermeasure also to obtain artificial gravity, either by centrifugation of the entire vehicle or simply of the astronaut, where you see here at the bottom of the slide to the right. We need to improve the physical training system, so involve new treadmills and squat machine, like you see this new Colbert treadmill that was tested during parabolic flight. And we need to develop a new set of medication called pharmacopoeia to counter the bone immunization and the immunodeficiency. With all this, I think that very soon we should be able to say that Moon and Mars, here we come. Thank you very much for your attention, and I would be happy to answer any question later on. Thank you.
Thank you very much, Vladimir. So I'd like to remind everyone that if you want to ask your questions, we have a short time now for questions, maybe 1 or 2 questions, and we'll have a round table at the end also where everyone can discuss with the speakers. So I will first start with one of my very own questions. Is there an ideal countermeasure, or do you think it should always be a combination of different things, because you cannot solve all the problems at the same time?
Yes, the ideal countermeasure would be actually to provide gravity. There's no discussion about that. If you can provide a gravity, whether the real gravity, so a mass, which of course would be impossible when you travel into space, but simulated gravity basically by having either an accelerated flight, so you will feel simply the gravity due to the engine pushing the vehicle forward, or by rotation, by centrifugation, then that would allow to alleviate a lot of problem on human physiology. Of course, that would not always be possible, and I think the reality, the thing towards which we would go for a long duration interplanetary flight of human crew would be a combination of gravity, artificial gravity inside the vehicle, and also additional exercising and also additional drugs that need to be taken. So it would be a combination, a bit of everything. So the astronaut would be submitted to centrifugation, for example, for a certain time per day, maybe half an hour, 1 hour, 2 hours, depending. And also, we don't know yet at which level, G level, would be sufficient to counteract all the effects, negative effect of microgravity on the human physiology. But I believe that would be a mixture of all these solutions that would need to be provided.
Thank you very much. So we have several questions about the time frame, the time scales, also about the questions. So you talked about some adaptations. Are these short or long-term effects? Are they temporary or are they permanent? Do we always reach a plateau, or are there some systems that during our 6 months missions on the ISS still do not reach a plateau and continue to decondition?
That's a very good question, and it's quite complicated to answer to that, depending on which system as well. As I indicate, for example, all the inner ear system, the vestibular system problem, usually that would disappear after a few days, and you get readapted when you come back on Earth after a few days. So that's not an issue. The heart problem, the cardiovascular system, there also you reach a new equilibrium while you're in 0G. You reach a plateau that is relatively stable, and you need to be readapted when you come back to another gravity environment on Earth or on Mars. That would take also some time, which would depend from one person to another, depends also on the exposure of microgravity before and so on, but typically it would take days to weeks, and in certain cases maybe months, but usually it's several weeks. The bone demineralization and the immunodeficiency, this is a quite unknown subject for the moment. We still do not know whether we reach a plateau in microgravity, long-term duration microgravity, because of course 6 months is long, but at the same time, it's not long enough. There was one mission which was called the 1-year mission a couple of years ago, where this kind of effect has been studied as well, and we could still see some evolution, but at a lower speed. So there is a tendency to get adapted towards a new plateau situation, but still with a slow evolution. Basically, all this said that human life, as we know it, is not made to be adapted, let's say, to a real microgravity environment. And we would definitely need a stronger countermeasure or artificial gravity.
Thank you very much. I see that there are many other questions, but maybe we'll keep them for later, and we'll move to the next presentation. Thank you again, Vladimir.
Thank you.
All right, then let's go to our second speaker, Dr. Bjorn Baselet, who is a senior scientist at the Belgian Nuclear Research Center, where he's actually a colleague. He's coordinating different space biology projects at the radiobiology unit, who is led by Professor Sarah Batu that you just met before. He has a master in biomedical science from Hasselt University and a PhD on radiation-induced cardiovascular risk from UCL. And with all his knowledge and experience in radiation, he's going to talk to you about how to increase radiation resistance in astronauts.
So hi everyone, as mentioned,
We don't hear anything. Sound is switched off.
Okay, so I'll start again. Hi everyone, my name is Bjorn, and I will talk about the biomedical countermeasures to protect astronauts against radiation. Before I start, I want to set the scene. So imagine you're out having an adventure in space. But as mentioned in my presentation, there are some stressors. There are things there that try to interact with us, and things that we cannot exclude. One of them is ionizing radiation. I work at the Belgian Nuclear Research Center, so I'm really interested in this kind of stress factor in space. But as mentioned during the presentation beforehand and this session, we also have altered gravity levels, but as well psychological stress due to isolation and confinement, heavy workload, or even differences in day-night rhythms. So all of these stress factors have some effects on the body of an astronaut in space. And as shown before as well, all these different stress factors will cause a difference, will cause an effect, will cause alterations, and some of them can turn out to be a disease. So we already heard about motion sickness and immune dysfunction, but we have many, many more that are caused by these different space stressors in a different environment than we are used to. Luckily for me, as I'm a researcher, there are still a lot of open research questions, so it keeps me going. One of the biggest questions is, how do these space stressors really affect our health? How do they cause these different diseases? And the other question is, how can we prevent them from even occurring? How can we get our astronauts safely, for example, to Mars? Can we have some countermeasures, like, for example, using a treadmill to protect them for certain effects like osteoporosis? So during my presentation, I will focus on these countermeasures. Before we go to radiation resistance, I first want to have a brief introduction about the space radiation environment. So the space radiation environment is really different than the ones we experience on Earth. We have three main sources of space radiation, which are solar particle events. So for example, protons coming from our sun as solar flares. We also have galactic cosmic rays. Imagine an exploding supernova many light years away that brings particles towards us. And we also have the Van Allen belts. These are geomagnetical belts that can also trap particles as they are also magnetic and can also give rise to a certain amount of radiation once we start to leave Earth. The thing is that in space, we have either more, but also more damaging kinds of radiation than we experience on Earth. So we're experiencing way more than we are normally used to. And this has an effect. One of the paradigms in radiation biology where I work in is DNA damage. We try to explain a lot by our DNA structure and how it gets damaged upon exposure to certain conditions like ionized radiation. So this seems a complicated picture, but I will run through it with you. So you see to the right, there are interactions of ionized radiation indicated by the red arrows towards us as being a set of particles. This can be either direct, so directly, for example, affecting the DNA, but can also be indirect by, for example, production of radicals, different kinds of aggressive molecules that can spontaneously form in interaction with ionized radiation in our body. And in such a manner, we can damage our DNA, and this DNA damage can, for example, give rise to cancer. Now, if we are going to talk about radiation protection, we have to talk how we can protect ourselves against radiation. Step one is stopping the radiation for even interacting with us. Step two is shutting down this indirect effect. As you know, we exist of a lot of water. So if we stop the interaction of our ionized radiation with water, we can also stop this effect of going towards our DNA. And then the third one is to stop the damage of being persistent. So repairing the damage that is done. If we look at the first level, stopping the radiation level, we have to say that there at the moment are known effective biological mechanisms to counteract ionized radiation from interacting with us. It's really difficult to stop irradiation or to shield ourselves. So, of course, we already sent some people in space, so we found some countermeasures, but they are either operational or engineering in nature. Operational, as the word says, it's just during the operation we make some rules. So for example, we say, okay, we'll limit the amount of time you spend in space. So you can only go for maximum 1 year towards the ISS and then you have to return. Or you're not allowed anymore to go outside the vehicle because you already have enough radiation entrapped. Then we also have the engineering countermeasures, and this means changing stuff, putting in shields, putting in materials to protect ourselves against radiation. So this is one of the things you mostly think on Earth, for example, with LED. On a space, they do similar work. Then we also saw level 2 and level 3. So stopping the loss or repairing our damage once we have damage done. The lucky thing for us and for me is that these second steps and third steps can be done on a biological way in an individual. So we can try to look at radiation resistance mechanisms in ourselves. So then it raises a question. So we're talking about radiation resistance, but what's radiation resistance? Well, how can you define it? Well, it's the capacity of an organism to protect oneself against or repair or even remove the damage caused by ionizing radiation. You know, we have a lot of different organisms on Earth, and we also have a different level of radiation resistance. If we, for example, look at humans, if humans would be irradiated with 4 to 5 gray, is a certain amount of dose of ionized radiation, this means that these people that were irradiated would die. If we then, for example, compare it to the tardigrades, which can endure 5,000 gray, or even the Deinococcus radiodurans, a kind of microbiological being living even in the water of a nuclear power plant, you can see that they are way more resistant than us. So there is something to learn from biology how we can cope with exposure to ionizing radiation. Recently, we helped writing a paper which defined a roadmap, defined a way how we could enhance ourselves from radiation, how we can protect ourselves against the different effects that radiation can induce. So I will go over the image you see here on the right, and I will pick up some points and some ideas on my way. The first idea is to have a selection. If we look at the human population, we see that there is a real individual response against ionized radiation. We are different, and we can take that difference and use it to our advantage to, for example, send only astronauts which are more resistant to radiation, just as a human being naturally. So the question still arises, can we include a test to determine the sensitivity of an astronaut? Is that ethically allowed, and can we exclude people from going to space because they're too sensitive? Another thing that we can do as well, and we are really good at it as a human being, is develop a pharmaceutical intervention. We can believe of some pharmacological compounds that we made to protect ourselves. For example, a radiation protector. At the moment, there is only one known radiation protector that is allowed to be used in the clinic, and that's called amifostin. However, there are many, many more molecules that can help ourselves against radiation and the effects of radiation. Another thing is a gyroprotector. It's a difficult name, but it's just a medication that stops ourselves from aging, from different adaptations to the environment. An example is curcumin or curcuma, normally a herb you use in your kitchen, which is also there to stop aging or at least decelerate it. Lastly, we can also think of redox scavengers. I talked about the indirect effect where we have these nasty aggressive molecules that can damage our DNA. Well, we can use, for example, ascorbic acid of vitamin C, which you can find, for example, in oranges. We can also take that as a tablet, and we can also try to protect ourselves against this DNA damage to occur. The third one is actually an easy one. You can also just go to space and go sleep there. While sleeping or hibernating, like you see this animal here doing so, it changes certain parts of our cells, of our metabolism. Now, we do not need a normal sleep, but we need a sort of dormancy state, where we are in a low energy state for months and months on end. Normally, we only sleep a certain amount of hours per day, but imagine if we could induce a sleep for 6 to 8 months. We heard about travel to space, it takes 6 to 8 months. Well, imagine if we could, for example, induce a sleeping state in these astronauts for 6 to 8 months, and they would wake up without having a lot of damage. The nice thing about this is that we need to send food and water, but imagine if you're sleeping for 6 to 8 months, you would eat less, drink less, so also we need to send less. That can also help us in the future to make it more worthwhile and more easy access. Another thing that we can do is we can send some spare parts. Imagine we talked about differences in heart, differences in muscles. Imagine if your heart stops working or is not working correctly anymore. We can just have a new heart ready in the freezer for you to use if your old heart fails. So at the moment, we're already doing a lot of research on Earth for that, to make new tissues, to have tissues at a standby. But the problem there is we need to store it. We need to have a certain cost, and it also brings some risks. For example, with liquid nitrogen, it can explode. Would you like to have an explosion on a rocket? I wouldn't, but maybe you would take the risk. Something different as well is you can also make fresh ones. So you cannot take the old, you cannot take ones from Earth, but maybe you can make them there in space. Imagine we would take some cells, we would grow them to, for example, form a heart or to form a skeleton, and we can also use that to heal you, to repair your damage that you have incurred due to radiation. Another idea that is also raised in the roadmap is the use of deuterium. Deuterium is a hydrogen isotope which is stable and which can be used and ingested by us. The thing is that organic compounds made with this kind of hydrogen, so we are composed of carbon hydrogen mostly. If we make organic compounds with this kind of bond, so the carbon hydrogen deuterium bond, it means that these links are stronger, so less easy to break, less damageable. So we could maybe think of heavy water as a radioprotective strategy. We can maybe drink this water at a certain amount before we go to space to protect ourselves. The last one, where you also hear a lot lately, is gene therapy. You could also try to look at other organisms, and you will find many, many different nice stories of genes, of things we already identified, which can protect ourselves. We can steal, for example, the antioxidants from a lemon or from an orange and implant that in us, so we make it ourselves. Or we can maybe accelerate our DNA repair. Maybe an organism has better DNA repair mechanisms. Maybe we can steal it and we can use it for ourselves, for our own good. Or I talked about the Deinococcus radiodurans, the organism at the lowest part of the presentation. We can maybe see why they are more resistant and also use that to our advantage and change our genetically to see how, if we can cope with the damage and if we get more protection against this radiation source. To end, I want to say that at the moment there is minimal research going on in this field. So we need still a lot of things under an investigation to really detect what's going on and if we can protect people with these strategies. As mentioned before, these are strategies for space to protect astronauts, but they can also be used on Earth. Imagine cancer therapy patients, they're also treated with radiation. We don't want their healthy tissues to get also radiation effects. So we can also have a certain value on Earth. And the last thing is that the things I mentioned during this presentation are quite speculative, but they are strategies that can form a foundation in the future, which can pave a road towards radiation protection and a manner how to keep astronauts healthy and how to send them more healthier towards, for example, Mars. So I end my presentation. I want to thank you for your attention, and you can pose the questions in the chat and hopefully they will ask me. Thank you very much.
Thank you very much, Bjorn. And indeed, we have already several questions in the chat. And I will start with the first one from Camilo. So imagine you want to become an astronaut and to give good arguments to be selected. How is it possible to know your level of radio sensitivity as compared to the general population? Is there a test you can do?
There are tests already available to look at your radiation sensitivity. So at SCK, we look into this, and we have, for example, a test where we look at the amount of DNA damage that is incurred on your cells. So what we could do is we take a blood sample, we extracted some cells, We irradiate that, and then we look at those cells, how they interact with ionized radiation. And we know already from the general population how they react, where the average person is, for example, and then we can see if you are equal or you make more or less than the normal standard sample. So in that way, we can already have a molecular test, let's say.
Thank you. So the second question is about the importance of twin studies, because twins are supposed to...
If I may, Jeremy, we don't hear you very well from the people who are following outside.
Okay. So the second question is about the importance of twin studies, because they, genetically speaking, they are very similar. How important are these studies? And a question maybe from someone that has a twin, are there some studies at the moment where they're recruiting some twins?
So a really good question. So recently we had the NASA twin study where one of the twins was sent to space, another one was used as a control. For me, it's a really nice study because it's difficult to have a control for an astronaut. An astronaut is heavily selected and is good in his job, but is also not part of the general population. They're healthier, they're more trained, they have a higher education background, they come from a better economical background. So it's difficult to have a proper control. Well, the nice thing about twins is, and monozygotic twins, so they have the same living, or they grew up in the same environment, and they also have the same genetics. So in that sense, we already have a proper control, let's say. The downside, of course, of this is that there are a lot of monozygotic twins that had the entire astronaut training. So I would really motivate people that are monozygotic twins to become astronauts and to go to space, but at the moment, there are not a lot. At the moment, NASA is continuing the 1-year study with the twins, but they are looking more into the normal astronaut population because I think at the moment there are not enough twins in the program.
Okay, thank you. And maybe we'll take a last question before moving to the next presentation. It was a question about the pharmaceutical intervention that you mentioned. When you go to space, the pharmacodynamics is changing. How could this affect the usage of this intervention for radiation protection?
You say disinfect or to distinguish them, you mean?
Because pharmacodynamics is changing in space. How can we study this, for instance, on Earth, where pharmacodynamics is different? What do you expect to change?
Yeah, it's a good question. So indeed, if you go to space, your pharmacokinetics, pharmacodynamics really change. So we have some models here on Earth, like the previous presenter already showed. You have, for example, the Bacterial, where we can simulate some fluid differences, or we have animal models, or even tissue models or cellular models, in which we can mimic the environment. We can simulate microgravity, stress, ionized radiation, in such a way that we can look into this pharmacokinetics. But at the moment, we do not yet know how astronauts and how our system as human is reacting in space. So we still need a lot more research in this field as well.
Thank you very much.
You're welcome.
So we're going to move to the next speaker, and I will let Kevin introduce.
So the two first presentation was all about humans. However, life science is not limited to humans. There are many different organisms, and actually they all play a crucial role into space exploration. And our next speaker is starting to talk about that. It's Professor Baptiste Leroy, who is assistant professor at the University of Mons, where he's working in microbiology and proteomics to study bacterial metabolism. More specifically, nitrogen metabolism in cyanobacteria and carbon metabolism in purple bacteria. And all his knowledge is sustained as well with a master in biology at University of Mons, as well as a PhD in animal behavior. And so he's going to talk about how bacteria can actually be used to produce oxygen as a supporting life method in space.
Okay, thank you very much, Kevin, for this kind introduction. Yes, indeed. Today I'm going to speak about how to support life in space and how bacteria can effectively be used for this in space. So I am a biologist. I will not be speaking about the astronauts themselves, but how to sustain their life during long-term missions. Of course, we have been exploring space for a long time now. We have been living in the ISS for months. We have been in city trip on the moon for a very short-term mission on the moon. Definitely the next step is to go on Mars. We already send robots on Mars to try to analyze a bit the surface of this planet, but definitely we need to send men on Mars. Mars is much far away than the moon from Earth, and as Vladimir already told us, going to Mars will take a long time. Vladimir mentioned that in worst case scenario, the one in which you use less fuel, it will take more than 6 months to reach Mars. Of course, you need to come back from Mars to the Earth, and you also want to stay there for a bit more than just 1 month. You need to explore this new planet. So one maybe logical scenario would be to imagine that if we want to go to Mars, we should imagine to stay there for 1,000 days. Almost 3 years. What about going there during 3 years? On Mars, you need to eat, you need to respire oxygen, you need water to drink, but also hygiene water to take a shower from time to time. All those needs, just to keep you alive in space, are estimated to be around 20 kilo per person per day. If you want to have a crew of 5 or 6 members, which is a minimum crew to go on Mars, and you want to stay there for 1,000 days, you immediately realize that the payload you have to send on Mars is enormous, just for food, water, and oxygen in space. So for the moment, are we really able to do so? This is an old slide I really like because it's not on SpaceX website anymore, I think. But a couple of years ago, on SpaceX website, you could see the payload capacity of the different kind of spacecraft they developed, and this famous Falcon Heavy spacecraft, which is the best launcher available today to send something in space. And this Falcon Heavy can launch on in low Earth orbit something like 60 tons of material. If you want to send something on Mars using this Falcon Heavy spacecraft, it's only a bit less than 20 tons that you are effectively able to launch in space. And the cost for such a space launch is really huge. Falcon Heavy launch cost $90 million. And the price were effectively present on the website, which is quite funny, I think. And there is still somewhere you can click on shop. And so apparently you can eventually already book your personal Falcon Heavy launch. But okay, so you realize that today we are not able to send just your launch packet on Mars because just the launching capacity is not there yet. An astronaut will require an habitat, some instruments to do exploration. So definitely this launch packet is too heavy. There is new technology that are also arriving. Starship spacecraft is being developed with on-orbit refueling, but definitely the weight of this launch packet will always be an issue if you want to go on Mars. So what could be a solution for this? What about recycling our waste? On Earth, no one needs to give you oxygen, water, or food because it's being produced all the time with our waste. This is the idea that has emerged a couple of years ago, 25 years ago, from ESA scientists. And they think, okay, we should try to inspire ourselves from ecosystem we have on Earth. And they decided to mimic the lake ecosystem in which waste are continuously recycled in order to give food to all the inhabitants of this lake. They developed some schemes of this ecosystem in which consumers, for example, the fishes, need oxygen and are producing waste, and those wastes are treated by bacteria, and those bacteria are producing basically fertilizing element for plants, and plants are producing food and oxygen for the fishes. This is exactly what has been developed in the MELISA project. The MELISA project is a combination of bioreactors that are inhabited by bacteria, and those bacteria have a specific role in treating true waste. Some of the bacteria will be responsible for organic waste digestion, anaerobic digestion, as if we want to produce biogas on Earth, we do the same kind of technology. Some other bacteria will be responsible for nitrifying the nitrogen source. And finally, the fourth compartment will be inhabited by plant and cyanobacteria that will do photosynthesis. Photosynthesis will allow producing oxygen, food, and removing the CO2, which is one of the major waste products from the crew. In the same time, those photosynthetic organisms will purify the water for the crew. So this project is now 25 years old, and this project is running a very interesting collaboration of multiple labs around Europe, all over Europe. We have different kinds of scientists, we have physicists, we have mathematicians, we have engineers, of course, and we have some biologists. I will not speak about a complete project today, but if you want to know more about this project, I encourage you to visit the MELISA Foundation website, in which you will find a lot of information on this MELISA project. Today, I'm gonna focus only on the oxygen production and CO2 removal that is being done in the fourth compartment, compartment C4A, in which we have cyanobacteria. Why do we have cyanobacteria there? Just because cyanobacteria are much more efficient in producing oxygen and in doing photosynthesis than our plants. If you just compare the protein productivity of cyanobacteria, so for example, this spirulina we are working on, this Arthrospira species, these bacteria produce protein 4 times more efficiently than the best plant can do. So it is exactly the same for oxygen productivity. If you have to deal with a certain amount of oxygen being produced on a defined surface, cyanobacteria are much more efficient than plants to do the job. So this is why the C4A compartment of the MELISA loop is being inoculated with cyanobacteria to produce oxygen and food in space. And we have already had this opportunity to demonstrate the oxygen production in space with these cyanobacteria. So of course, sending a bioreactor in space is not that easy. This Artemis project was led by our colleague from SCK, and very recently they demonstrate for the first time that effectively we are able to operate a bioreactor, a very small bioreactor with cultivation chamber of only 50 milliliters, so it's very, very small bioreactor, but it was already an enormous achievement. Before this, we had first to analyze the behavior of these bacteria under ionizing radiation, for example, under simulate microgravity, and in different kind of conditions. But indeed, the MELISA group, the MELISA consortium, has been able to produce oxygen in space a couple of months ago, and it was the first photobioreactor sent in space ever. So what are we doing now then? In fact, in the MELISA project, we don't want to work with black boxes. A bioprocess, for example, oxygen production, a bioprocess can be analyzed as a black box. We just put light on the cyanobacteria and it's producing oxygen. But we don't want to work with those black boxes. The biologists of the MELISA project want to open those boxes. Why? Just because we need such a level of safety in the bioprocess we are developing for space that we need a very high level of understanding of the bioprocess we want to use and we want to control. And to try to convince you that we really need this deep knowledge of a bioprocess to be able to control it, I propose to have a very short video. I hope that all your connection will be good enough to see this video. So in this video, we will look at a hurdle race. In a hurdle race, if you want to predict who will be the winner, when you do mathematical modeling and a black box strategy, you are just looking at how did the runner run last time. You take that time and you say, okay, this one is running this fast, he should be the first one. And you can predict the final podium like this. But in a bioprocess, things can be a bit different. Look at this guy on the second corridor. He's starting to make a job which is not supposed to do. And this bioprocess is somehow escaping the rules, but it's not only that he is, this bioprocess, changing his own action, he is also having an influence on the rest. This video is a way to show you that if you need to have large capacity of control, you also need to have huge understanding of your process. This is exactly as the example of Jeremy with the frog and the leg. Just think that cutting the leg of the frog make something on hearing capacity of the frog, you are mistaken. This is exactly the same process. We need to have huge understanding. And this is why today you have someone working on bacteria metabolism that is speaking about space. In space, we also need to have huge understanding of the bioprocess we want to analyze. And this is what we are doing at the University of Mons. We are working on omics, so we are mainly doing proteomics and metabolomics using mass spectrometry and NMR in order to understand how bacteria are responding to their environment. It can be space environment, so how bacteria responds to radiation or microgravity, but it can also be in order to better understand the bioprocess we want to apply in space. And this is what we are doing in the BioRat2 project. In the BioRat2 project, we are trying to go a bit further than just producing oxygen in space. We are trying to evaluate what will be the consequences of changing the nitrogen source we apply to the bioreactor, and can we have this new degree of freedom in the bioprocess to be able to play not only with the light to control the oxygen production, but also taking into account different nitrogen conditions. And we have been working on this BioRat2 project for the last 2 years. And basically what we are doing is that we are putting those cyanobacteria in different nitrogen conditions. It can be nitrate, ammonium, urea. We are testing different conditions that could happen in space. And we are trying to understand how they react. And based on their reaction and on their metabolic answer, we are building models that allows us to predict their behavior more accurately than just doing increase or decrease of light intensity. And this BioRat2 project was supposed to end up with a ground demonstration that we have done a couple of months ago now. And in this ground demonstration, the idea was to be able to sustain the oxygen needs of a consumer compartment just based on the bioreactor where cyanobacteria are cultivated, and to keep controlling this bioreactor even if we change the nitrogen source and we change the environmental condition to which the cyanobacteria are exposed. And so we did it a bit, it was a bit homemade demonstrator, a breadboard, with a lot of electronics to have sensing oxygen, CO2 level in the consumer cage, and the system would adapt itself the light intensity given to the cyanobacteria so we can produce the oxygen which is effectively required by the consumer. And as a consumer, we had a crew that we had in our very simple Melissa loop, which was a mouse. And this mouse has been kept in this completely airtight cage for 6 weeks. And during the 6 weeks, we have demonstrated that we could provide all the oxygen required by the mouse just using a bioreactor with cyanobacteria inside. And so we could demonstrate that based on the knowledge we gain on nitrogen metabolism of the bacteria, we are able to predict how much oxygen they will produce, even if we change the nitrogen source and the environmental condition we are exposing the bacteria to. So this is a first step. Now we want, in this BioRat2 project, the idea is now to go one step further and trying to treat directly urine. As we have gained more knowledge on the nitrogen source we can use, we want to treat directly urine to have some kind of simple Melissa loop in which we just treat urine to produce oxygen using cyanobacteria. Of course, we already talked about this a bit, and Jeremy already shown us that investing money in space is something which is highly interesting because you have a payback, which is very, very important. But each time you speak about space research, you always have to demonstrate that there are also terrestrial applications. And of course, there are a lot of terrestrial applications, and I just want to share with you 3 examples of this. One example is a project that we are running for the moment, which is called the Purge to Value project, which is linked with the knowledge we've gained in this space research. And in this project, we are working with HBC Biberach in Germany, and with a Thai company, Energaya, in Bangkok. And this Bangkok company is producing cyanobacteria for food, because cyanobacteria are very very high nutritional value. And so it's very interesting as a food complement. And they are trying to produce cyanobacteria on rooftops in Bangkok. And thanks to the knowledge we gain on the metabolism of cyanobacteria, we are now developing solutions to recycle water in this cultivation facility, and in order to make the water consumption very, very lower in this kind of bioprocess. Another very exciting project we just submitted last week is the Mars project, in which we would like to build on a new building of the University of Mons, a photobioreactor facility that will allow fixation of all the CO2 that the heating system will emit. So the idea is to develop some kind of biofacade or biofacilities, bioroof, call it whatever you want. But the idea is to be able to capture all the CO2 emitted by buildings. It's effectively to try to face climate change, and it could also be possible normally to develop buildings that are at negative emissions, so fixing more CO2 that they are emitting. And a final project that we have been submitting with some colleagues from north of Africa, also related to nitrogen metabolism of cyanobacteria, is to be able to use food industry waste in order to produce food again. And so producing cyanobacteria as a food complement, in particular in North Africa, in order to decrease the waste that are just released in the environment by the food industry, and making food again with this waste. With all this, I will complete my talk, and I will first thank all the partners that are working in the MELISA project. It's very fantastic journey, because we are working with diverse persons. And I would like to encourage you, if you think that you could be helpful somewhere in the MELISA project, because we need so many different kinds of scientists in the MELISA project, just visit from time to time the melisafoundation.org website, because we are quite often recruiting postdocs and PhD students. Thank you for your attention.
Thank you very much, Baptiste. We have again some questions. And the first one is from Paola, asking if genetic mutations caused by the space environment could affect the cyanobacteria efficiency by modifying the metabolism.
Yeah, that's definitely a very good question. Of course, mutation will affect the metabolism and the behavior of the bacteria in space. That's completely clear. But mutation also affects metabolism and behavior of bacteria on Earth. So we also know that when we develop some bioprocess, bacteria gets adapted to the job you ask them to do. And nature is always selecting the best player in any field. And so if you have some bacteria that have to do a job in space, of course, they will adapt to what you are asking them, or to the environmental condition you are putting them in. So definitely bacteria will change. Definitely metabolism will change. The idea is to be able to monitor it and control it properly. There are lots of solutions of changing the bioprocess in order to still target the function you want to have. But yes, definitely bacteria will change, but they are also changing on Earth.
Thank you very much. So you talked a lot about CO2 and O2. If we want to close the loop that involves food production, you said, in the movie The Martian, we saw that they were cultivating potatoes. What kind of vegetables are the most efficient for the future astronauts?
So I'm not an expert of this kind of questions, but yeah, there are a lot of selection has already been done in what kind of plant have to be cultivated. The selection is not only done based on what plant is growing the faster or being the most resistant to radiation and whatever, but also to psychological effects. So for example, you need, if you want to go on space, to have some variety on what you are eating. And so I know that tomatoes, for example, are part of the list. Lettuce, because it's easy to grow. Wheat, because we need to have bread somewhere, because it's something we use to eat on Earth. And so there are also some psychological elements that have to be taken into account. But yeah, the main one will be tomatoes, potatoes, wheat, lettuce.
Okay, thank you very much. So now it's time to go to the next presentation, and if you have other questions for Baptiste, you can still ask them in the tab, and we will talk about this at the very end. But for the moment, let's go to the next one.
All right, time is flying. It's so interesting. The next talk will be from Professor Karine Van Doninck, who is a full professor from UNamur. He's also founder of the Laboratory of Evolutionary Genetics and Ecology, sorry. She has a PhD in biology from the VUB, and during her first postdoc in Harvard University at the lab of Professor Matthew Messelson, she discovered the bedyloid rotifers. This is quite an amazing small organism that she will talk about it. And she had a second postdoc at GMIERD with Dr. Yanis Michalakis from France. And because of a love about the bedyloid rotifers, he continued to study them regarding their resistance and their asexual evolution. So the floor is yours.
Okay, everything fine? Perfect. Thank you very much. So today I hope I will convince you that we have somehow found or discovered, and nature is probably full of it, some very interesting small microscopic animal, the bdelloid rotifers, that can be very interesting for space research. So first of all, what are bdelloid rotifers? So what you see here is a microscopic animal with a full digestive system, nervous system, and these are females. So bdelloid rotifers are small animals only made of females. You see here the digestive system, and on both sides, they are reproductive organs of females, meaning that's how we recognize them. So here you see, this is the female, you see the reproductive organ, and you see inside this oocyte, these germline cells. And so one oocyte can form an egg that is laid by the mother that starts to divide and a new individual is formed. So we have organisms here that are cloning themselves. So they reproduce without males, without sexual reproduction. And somehow this is an evolutionary scandal, because we know that to evolve and to adapt, you need to diversify genetically. So if you clone themselves, how can you diversify into more than 400 species as we found in bdelloid rotifers? So this is one important puzzle we are studying in my lab. A second interesting feature of bdelloid rotifers is the fact that they are extremophiles, meaning they can survive complete desiccation. So what you see here are lichens on trees next to our park at the university. So we sample them, but you see these lichens are completely dry. Still, they are filled with life, including bdelloid rotifers. So when we bring this to the lab and look at it, what you see here are little tons. These are little bdelloid rotifers that are completely dried up. When we add water to these lichens, including those bdelloid rotifers, after a while, they start to rehydrate to continue their survival and to reproduce. So these animals, in fact, cycle between a hydrated state when they reproduce and survive, and when water is gone, they go into this desiccated state where the metabolism is completely stopped. In desiccated state, we can keep them months, years, we can freeze them till -80. They do fine when we add water again. And we also discovered that besides this desiccation resistance, they're also very resistant to ionizing radiation. So here you see a recent study by my postdoc Boris Espils, where he exposed these Deloitte rotifers to different ionizing radiation sources, proton radiation, X-ray, and iron particles. And you see that they can survive these till 1,000, 2,500 gray very easily. If you remember what Bjorn presented, for humans, 10 gray is already a lot. So very few animals can survive such high doses of ionizing radiation. So we may wonder, how can you adapt to ionizing radiation when you're not exposed to it on Earth? So there is probably a link with their desiccation resistance. So remember, since we have an animal that can clone itself, we can easily culture in the lab and have many replicas of the same genetic material. We desiccate these animals in the lab, and then we look at the impact on their genome, on their genomic integrity. And what you see is that the longer these animals are in a dried state, the more their genome is broken into pieces. So all their chromosomes, their genetic material gets broken up. But when we rehydrate them, they start to repair their broken DNA. If you look now at the impact of ionizing radiation on genetic material, like Bjorn was showing, ionizing radiation, if we add that on desiccated rotifers, it breaks the genome into pieces. And at 800 gray of proton radiation, all your chromosomes are broken up. So you have a huge damage to your DNA. In Deloitte rotifers, when we do that, we dry them up and we irradiate them, they do fine, they survive very well. And upon rehydration, they start to repair this broken DNA. And it's not only in the desiccated state that they are very resistant, also in a hydrated state. So here in red are desiccated animals, here are hydrated animals. And at even 1,000 gray of X-ray radiation, these hydrated rotifers still do fine in their survival. If we look here on the reproductive capacity, we see that this goes down, but you need to go till doses higher than 1,000 gray to really lower down their reproductive capacity. So we have shown that survival is high to this ionizing radiation. Their reproduction at some point is lower, showing that the germline cells of these Deloitte rotifers are less tolerant to the damage induced by ionizing radiation than their somatic cells. But you immediately see here that it's an interesting model system to start also to look at their repair mechanism. And this is work done by Boris Espils within our ESA projects, but also by postdocs in my lab like Mathieu Terwine. So we have been looking here at the profile of the parental line that we have cut with a restriction enzyme. So you see here the parental line, the profile of the genome. And when we let them repair, we see that slowly they start to repair the parental line within 48 hours. So these animals do repair this damaged DNA after radiation within 48 hours. And interestingly, when we look at the descendants after ionizing radiation, so the mother have cloned themselves, we see that the genome has been perfectly repaired. The descendants here have the same genome again as the parental line, while it was at some point completely broken. So this is an animal that you immediately see why it could be an interesting model organism for space research, because we know that the space environment is hostile, like Bjorn presented. So I don't need to spend too much time here, but as shown before, there is a lot of radiation in space. So if we plan to do these long human space missions to Mars or long periods on ISS, humans will be exposed to higher doses of radiation, including ionizing radiation, with consequences at the DNA level. So you need a model organism to understand how do they cope with this extreme radio resistance. And so the first experiment we sent to ISS with the Bdelloid Rotifers was last year in December 2019. So here you see we inject 10,000 individuals per bag, and we had 10 bags going to ISS and 10 bags kept on ground. Remember, we have a very easy system here where we can send millions of individuals in space and have the same genetically million individuals on ground. So we can do a perfect comparison. We had 2 teams in Kennedy Space Center integrating all these individuals in the different bags that were then put in the module that was built by Kaiser Italia. So this was a collaboration, of course, with physicists from UNamur and from the Nuclear Center in Mons, with biologists, with engineers from Kaiser Italia, and with ESA. But interestingly, we did not only send a scientific experiment to ISS last year, we also added on the labels of each experiment an artwork. So we have a collaboration with Angelo Vermeulen, who is also in the Melissa project, and with the SEEDS network to send this artwork to space. It's called Engines of Eternity, and this artwork will evolve with the scientific work. So the scientific results will also be represented in the evolving artwork. You can go on this website to see more of it. But so to show you that these space projects is really an interdisciplinary project where you have physicists, biologists, engineers, even artists collaborating together to realize those projects. So here you see the 2 models on the tables that were sent to ISS with these 10 bags with Bdelloid Rotifers. The launch was on the 5th of December, and it arrived a few days later on the ISS and was put by Luca Parmitano into the cubic incubator. During the whole mission on ISS, of course, the temperature was recorded and followed and kept at 15 degrees, and the same temperature control was happening on ground. So we have a perfect replica here of an experiment on ISS and an experiment on ground with individuals who have the same genetic material. When they came back in January to our laboratory, we first of all checked if these animals survived during these 2 weeks in space, whether they laid eggs, which was all the case, so they survived, they laid eggs. And so then we started to analyze. The first thing we are analyzing, and today is the first day we show these results, is in fact the gene expression, to see if some biological processes are more expressed when they are experiencing 2 weeks on ISS. And these were analyses done by postdoc Victoria Morris. So first of all, what we see here is that somehow there is a difference in this expression pattern between the 2 teams, which can of course occur. So that's why it's important to have many replicas in your experiments. And then you also see that there is a difference in expression between the flight in blue and the ground. So we analyzed the 2 teams separately. And what we see, interestingly, is that there is a downregulation of genes in the flight samples, meaning that somehow the metabolism is lowered when they are on ISS, when we compare it to the ground samples. So you see the ratio of upregulated genes compared to downregulated genes is much lower than even 0.5. If we see, on the other hand, in these upregulated genes, so these genes here that are somehow upregulated when on ISS, we see that what comes up is this oxidative stress. So they do experience oxidative stress still when they are on ISS. When we compare these 2 experiments we have done on ground in our laboratory, so when we expose these animals to 500 gray X-rays in the laboratory, and then we look after radiation at the expression of genes, we see that there we have much more an upregulation of genes. So really showing that on ground level, there is this upregulation, that in ISS we had somehow a downregulation. But if we look at this upregulation of genes after radiation, after huge doses of radiation, much higher than what you experience on ISS, luckily, we see that these repair genes are very important. So you see a lot of these repair genes expressed after high doses of radiation. We are, of course, looking now much more into detail in which repair mechanisms are going on, are being used by these animals to repair the damaged DNA. But this brings us to the second experiment we are sending this year to ISS, is that we want to see if when humans are in space, when astronauts are long periods of ISS and they experience DNA damage, is their DNA repair mechanism still active, which is very important to continue repairing your DNA while being on long space missions. And so the Bdelloid Rotifer is a perfect system here. And so we have designed with Kaiser Italia a second model for the ROP2 experiment. So you see here the ROP2 model. So what we will put here at the bottom in number 7 is a dried patch of Bdelloid rotifers, so thousands of Bdelloid rotifers that are dried, that we expose in the lab to ionizing radiation, so their genome will be completely broken. We keep models on Earth, and models with the same animals go to ISS. And at the same moment, they will be rehydrated on ISS and on Earth. And then we will see whether they can repair their genome as well when they are in space as on Earth. On Earth, we know they do repair their DNA. What about when we are in space? And so my lab with a few of the postdocs, the two main postdocs that really headed this project of genome sequencing, is that we have also sequenced the first genome of these Bdelloid rotifers. And we obtained nowadays a chromosome scale assembly, meaning we have the 12 chromosomes of this animal completely assembled from one end to the other end. And this is very important if you want to study genome dynamics after being exposed to radiation or after a flight mission. So what we plan to do when this ROP2 experiment comes back from ISS is to isolate all these females that have been repairing on ISS, collect the eggs from each of these females that can be used to start a new clonal culture. And then from this clonal population, look, do we see that variation happened at their genome level? What about on Earth? Do we see changes on Earth at the genomic level? And what about space? Were they able to repair as well their DNA in space as on Earth? So this will be a very important question to look at this. Besides, we are also looking within other projects at how they deal with oxidative stress. So next mission in November 2020, if everything goes well, we are at least ready to launch it. And then in 2024, these animals will be put outside of ISS to be exposed to the entire space vacuum and see if animals can really survive in these extreme environments and how they cope with this. So I hope I have convinced you that rotifers are an interesting extremophile model organism to study the impact of radiation and microgravity on biological processes. If you want to follow more, we have this website of Rotifer in Space. Thank you.
Thank you very much, Karine. So the first question that comes in mind is, where can we find these rotifers in the wild? Where do they live usually before you study them?
They live everywhere, in fact. If you go into your rain gutter and you take some leaves there, you will find rotifers. If you take mosses, if you take lichens, maybe even in your drink water, they are everywhere. They also live in Antarctica in these kind of extreme environments because you can freeze them. They survive high radiation doses. So they're really found in all kinds of environments that we also call semi-terrestrial, so that are sometimes dry, sometimes wet.
Okay, thank you. And do we have an idea of how these rotifers are repairing their DNA? Is it a behavior that is also observed on more complex organisms, maybe even humans? Do we know how to translate this to humans?
Yeah, certainly. So what do we see when we have analyzed the genome? But yeah, in 15 minutes, I could not present all this. We have analyzed all the repair pathways that are present in Bdelloid rotifers. And they have exactly the same repair pathways and the same genes involved as humans. That's why it's such an interesting model organism. So they have this typical NHG, homologous recombination, all these pathways. The thing is interesting is to see which one is really active during repair. And then also, it's not that they have a new system, I don't think so. While there is one postdoc in my lab, Emilia Nicola, who has developed an interesting technique, the IPON, to really try to catch the proteins at the moment of repair. to see if we see something new. If there is one specific protein of the whole repair pathway that is maybe more efficient in Bdelloid rotifers than others, and this could be very interesting to then implement further.
And how close to the DNA repair system the one of rotifers is from the one of humans?
So what
are the similarities between the repair system of the rotifers as compared to the one in humans?
Well, it's the same genes involved. So the typical genes that are critical, for example, I think about RAT51 in homologous recombination is present and active in Bdelloid rotifers, or the other, or ligase present in the base excision repair is also present in rotifers. So we really see that these different genes involved in the pathways of human repair are also there in Bdelloid rotifers and are active. When we look at the transcriptome, they are really highly expressed.
Okay, thank you. So last question, and then we will go to the round table, even though it will not be a round table because of the restrictions. Do we know to what level of radiation were exposed the samples in the ROB1 mission so that we are able to reproduce exactly the same condition, the same radiation on Earth?
Yeah, that's a good point. Yeah, we need to have indeed the measurements exactly on ISS, so we can certainly have this. We didn't analyze all the results yet of ROB1, but indeed that's a very important one, because the question we now have of ROB1, we were 12 days in space. We see that the metabolism is somehow lowered. What we should redo is do the experiment on Earth in a much longer microgravity. So just already see if long periods of microgravity continues to lower this metabolism, which can somehow be a problem if you start to express less and less genes when you are in a long period of microgravity. So this first ROB1 experiment really suggests some additional experiments to better understand what's going on.
Understood, thank you. And now it's time to go to the round table. So I have some questions already, but if you have some, I would say, open question that anyone can answer, or if you want to target a speaker, don't hesitate to do so either in the discussion or in the Q&A section. I will launch this with a first question, maybe more targeted at Vladimir. So we know very well how the body is working at 1G. We start to know quite well how everything is working at 0G. What happens in the middle when you go to the moon at 1/6 of a G, or when you go to Mars to 1/3 of a G? We know that the body adapts to microgravity, but when they come back, then you have some problems. If we send humans to Mars, do we expect that the level of gravity would be sufficient to have problems? Or would it be close enough to 0 so that the astronauts don't have any problem?
Thank you. This is a very good question. We don't have answer to that question yet. Really, it's at the heart of the research today. To a point where there's still question that was asked already years ago, and to which we do not have the answer yet, to which the question is going like this: at which level of microgravity does 0G effect really start? Is it really 0.00 G, or is it 0.1 or 0.15 or 0.2 or 0.3? You see certain microgravity effect on human physiology. We still do not know exactly. What we know is that certain subsystem of the human physiology, even at cellular level, even at biological level, would start to behave like it would be in perfect 0G at a slightly higher level. So typically 0.05 to 0.01. For the human body as a whole, it is also hypothesized that the 0G effect may start around 0.15 G. So typically this is just below moon gravity. What we know from the Apollo mission is of course something already very important, but what we know is that these astronauts stays only a few days or up to a week or two on the moon, so not long enough to see the long-term adaptation to a very reduced gravity environment like on the moon, 0.16. This also is hypothesized to see that some of the astronauts made some, let's say, bad guess or bad estimate of distance and of slope, although being all or nearly all of them test pilot, which was quite surprising also at that time. So of course now, 50 years later or plus 50 plus years later, we start to see in retrospect that maybe the microgravity effect does not really start at zero, but could start already before reaching zero. Now, in terms of readaptation after spaceflight, this is interesting as well, because it may mean that we don't need to go down so low into microgravity that it would be sufficient to study human body at a reduced gravity, not exactly zero, but let's say slightly reduced up to 0.1 or so. What does it mean in terms of readaptation afterward? Again, we don't know, because we did not do experiment on long duration exposure to microgravity or reduced gravity. We have experiment on the ISS where the microgravity environment is near zero, typically 10-2, 10-3 or so. But to make long duration study on the moon gravity or Mars gravity, well, we need to go to the moon and we need to go to Mars to see and to study that. So basically, the question is still open. Answer is unknown.
Thank you very much for your answer. Even though, yeah, we still have a lot of unknowns. I would like to actually forward these questions a little bit to Baptiste, asking, so you are designing your systems in 1G, maybe testing them in 0G. How do you make sure that this will work anyway for astronauts going to Mars when they will have to work in different environments?
Yeah, definitely for the moment, the only thing we can do is make some testing in the ISS, and it's already a huge journey to get there, because you need years to prepare an flight experiment in the ISS. But we already have some data showing that, yes, indeed, the biology, so the metabolism of bacteria is affected by microgravity and radiation, but not that much. One of the main issues to work in space is the capacity, the mixing capacity. It's very difficult to mix your bioreactor in space, and what is the most important issue when you want to produce oxygen in space is the separation of gas and liquid, because the oxygen you produce will just not be on top of your bioreactor in space because they are not top anymore. And so this is a major challenge that has already been tackled by the SCK team in this Artemis project, because they developed some membrane bioreactor, and we are studying a lot those exchanges of gas and liquid. Regarding the metabolism of bacteria, yes, indeed, we need to study them more in space, and so we need to have more access to space flights. That's for sure our goal for the next few years. But normally, the bacteria are not affected in terms of metabolism itself. It's the environmental condition around the bacteria which is changing because of the lower mixing you can have in space.
Thank you very much. So since we're talking about Mars exploration, let's go further on this topic. For future long duration missions, we'll have a lot of new knowledge, especially on the genetic field. Can we imagine that in the future, we select astronauts that are genetically better in terms of resistance to microgravity and resistance to radiation? And I would like to ask this question to Bjorn.
That's a really good question. I think at the moment we're already there. We can do some tests and we can see the radiation sensitivity, but it's not a question, can we? But I think the question is, should we? Should we select astronauts to certain markers? Is it ethically allowed to do so as a generation, as a community? So we can, but the real question for me is, should we?
Yeah, that's true. There are a lot of ethical problems linked to the exploration of Mars in general, and to also selection of astronauts and so on. So we see that before going there are a lot of gaps in knowledge and technological gaps as well. And one of them is, how are we going to make astronauts live during such a long time, and that's the subject targeted by the MELISA project. I would like to come back to you, Baptiste, to ask you what are, at the moment, the big open technological gaps? What remains to be done so that we can have an independent spacecraft with astronauts living there, I would say not forever, but independently?
Yeah, so something I did not present because I do not have time is that there is also, for the MELISA project, there is the MELISA pilot plant, which is being built in Spain. And in Spain, they are, in Barcelona, they are building bioreactor that will be able to treat the waste or the waste product for one man in real size. And these bioreactors are being integrated on now. And some of those bioreactors have been running for years. And so we have a huge knowledge on how this process is effectively working on Earth. Most of the bioprocess have been demonstrated on Earth. What we still miss is, okay, how are we able to implement this kind of solution on Mars? How will those organisms effectively deal with ionizing radiation? How easy will it be to restart the culture we will have prepared a long time before reaching Mars? So all this still have to be fine-tuned, but the basic process is working. The question is now how to minimize energy cost, the weight of all those equipment, and how to adapt this equipment to space. But basically the principle is working on Earth. It also depends on the level of recycling you want to have. You can imagine that you do not have to recycle 100% of your waste. If you already recycle part of it, if you already produce part of your food, part of your oxygen, you already remove part of the CO2, you already save a bit of the payload you have to take with you on Mars. So it depends on what kind of level of recycling we want to achieve. But the process is already being demonstrated on Earth, almost completely closed loop. The question is, how far will we go for recycling and how we will make this huge equipment adapted to space constraint of energy and weight. A last point, which is still a bit to be tested, is the accumulation of micropollutants in this closed loop, because you are recycling element all the time, but there are some molecules that will be more complicated to degrade, like hormones, like medication, and those molecules could accumulate in the loop, and this is still something that needs to be deeply analyzed.
Thank you. And now I'd like to ask a question to Karine, which is, so once we understand very well how the rotifers are behaving, what is exactly the cause of their good resistance to radiation, how is it possible technically to transfer this knowledge to applications on human beings in radioprotection?
Yeah, it's a question I often get. So first of all, I'm a scientist in fundamental research, so I'm mostly interested in the answers, maybe less in the applications. But of course, something people are interested in. So first of all, what we discover is several things. Rotifers are not only efficient in repairing, but what we have discovered, and I cannot say all the details because nothing is published yet, but we found really that they can use molecules that prevents oxidative stress. And one of the main problems also up there, and that's creating also a lot of damages, is how you deal with oxidative stress. So Bjorn was showing, since we are filled with water, we create a lot of radicals that attack our proteins, our DNA. So rotifers, the most important mechanism probably is that they prevent this formation of radicals. So they probably lower the damage on their proteins, and so they keep their repair proteins active, which is probably not the case in other organisms. So it's not that they may have developed a new repair mechanism, it's more that they have a protective mechanism of their proteins, so they remain active to repair once they are exposed. And so of course, these molecules to prevent the formation of radicals are very interesting to analyze and maybe to implement and to apply then in a way or another, like we apply on medication, is how you could use these molecules of preventing radicals formation in human applications.
Thank you. And maybe Bjorn, you have a comment on how we can copy what nature is doing to protect the future astronauts in space.
Well, I guess we need a lot of fundamental researchers to look into different complex matter to really distinguish the genes we need and the things we need as a human to be able to complement ourselves. So for that, we still need a lot of different fundamental studies going on. We have already some parts of the puzzle, but we're not there yet. That's why we also have a roadmap written to steer people like the lab of Karine to really see where we can fit in and where we still need some parts of the puzzle to make it as a whole to really be able to protect people in the future.
Thank you. So if you have other questions, don't forget you can ask them in the chat. And for the moment, I will go with, again, another question to Baptiste, which is, are there any byproducts from the generation of dioxygen from cyanobacteria that cannot be used in the loop and that need to be dealt with in the process during maintenance and so on?
Yeah, so first, the main byproducts of oxygen production is the biomass itself. So bacteria are just growing when they produce oxygen because oxygen this is what we need, but this is the cyanobacteria byproduct. And they use photosynthesis just to build biomass. So biomass is the first byproduct, but fortunately, this biomass is edible and can be eaten by the astronaut and is of very high nutritional value. So this biomass is not a waste at all. One compound that can accumulate in the culture medium is sugar. So bacteria are also releasing a lot of sugar in the culture medium, and when you harvest the biomass, you end up with after a number of cycles of cultivation using the same water all the time, you end up with some kind of slimy culture medium and water because it contains a lot of sugar. So in space, the idea is just to trash this in the first compartment in which anaerobic digestion will destruct this. On Earth, we are trying to use those sugar to produce something else. For example, using yeast to produce oil from those sugar and then producing some biocarburants, for example, biofuels. And so, yeah, there are some other byproducts, mainly sugar, but in space, we can deal with them very easily by just digesting them in the first compartment.
Okay, thank you very much. And maybe we'll go to the very last question. I would like to target Vladimir for this one. So we talked about life science in general. Life science is many different things. We talked about physiology, but there is something that we did not discuss is about psychology, and I would say, and many scientists say that maybe science, I mean, like I would say hard science will be the easy part when we go to Mars. And the thing we will have little control on is actually the psychology of the future astronauts when they go there. Can you maybe develop on the consequences of life in space on the psychology and of the astronauts?
Yes, actually, if you allow me just one little correction, when you said hard science would be the easy part, I wouldn't be so sure of that. I mean, but that's okay. It's just a matter of a figure of speech. Now, for the psychological part, yes, of course, there are several stressors that will still be there. The main one are the isolation, confinement, and the fact that you have also always the imminent danger that you know it's always there. You may encounter a meteorite, or you may have a depressurization due to whatever accident, and so on. So you know that there is a potential stress due also to permanent risk that is there. Isolation and confinement is something that you can train for. You can train the crew well by doing some sort of simulation campaign here on Earth. You put them in extreme environment, either in poles or on top of mountains or underwater for a certain duration of time, without any contact with the outside world, and that basically would allow to train them. Although, of course, it's not exactly similar to a real space environment, because again, you don't have the same amount of risk that is always applied to you for quite a long duration time. Then there's also the fact that after some time in the mission itself, in the long duration mission, after several months, for example, you may have different type of feelings that would appear. like for example, you get bored into what you want doing because most of the work would be repetitive. Personally, I do not believe that, because astronauts are always explorers, so there's always new things to see, to understand, to study. And the other point that could be also is that you may develop some kind of conflict with your fellow crew member. This also can be trained for, in a sense that, again, you do not select individual and then assemble a crew. You selected crews that already function together well. So you put them again here on ground into a different kind of extreme environment altogether. And if the group dynamics, if the interrelation between the different team members is positive, is constructive, then eventually you find a good crew that you could eventually send to Mars. If you, on the contrary, have a crew that does not function well, then you have to disassemble the crew and reassemble somehow differently. And there is different psychological or psychometric techniques, let's say, that can be used to assemble different type of personality together to make sure, although you can never 100% be sure, but you can improve, let's say, the chance of success by assembling people that would go along well together. This, of course, is purely human psychology, nothing to do with real microgravity by itself, but it's still, again, microgravity is another stressor in terms of effect on the body, and you can feel that your body would react slightly different. One more thing also, the body fluids shift toward the upper part of the body, so mainly the torso, but also the brain, the head, would also affect the brain because there would be a slight overpressure in the brain. We do not know also the very long-term effect of this overpressure in the brain. Some people, some scientists think as well that we are thinking differently in space, in microgravity, due to this overpressure. Some people say it was maybe due to radiation as well. Still a lot of questions that need to be answered, and this is the beauty of science, of course.
Yes, indeed. I would like to thank you very much, to thank all the speakers for the very nice presentations, but also the answers to the questions. It was, I think everyone appreciated a lot, and I think I'm not the only one with this in mind. We reached now the end of the questions, so I would like also to thank everyone who attended this session today. I would like also to remind that it is not finished. There are other days. Switch to Space continues. For those of you who are interested, I invite you to come back tomorrow and the day after and the day after. Space, as I said, is a topic, a multidisciplinary topic. And if you want to really know everything about it, you need to be able to understand what happens in life science, but also physical science. And also, if you want to become a scientist, you need to know what is behind this, the economy and all these things, the potential applications on the Earth and their impact. So that's why it's so important to be able to deal with all these things. So with these words, I would like to thank you again. And to say goodbye, and I hope to see you soon. Because the world of space also is quite small, so at some point we all meet. See you.